Welcome to True Projects. In this video, we are going to explain about the project that is an efficient net YOLO network with CSPCBAM, Ghost, and cluster NMS for underwater target detection. Before getting into the execution, first let us understand what is the project about. So, the demand for marine resources has been growing rapidly, right? And with that, we have seen huge strides in the technology for detecting things underwater. This has led to the rise of intelligent underwater robots that can identify and monitor marine life like sea urchins, starfish, sea cucumbers, and scallops. These robots are becoming essential and not just for making sure that we use marine resources responsibly, but also for critical areas like military operations. But here the challenge is underwater detection isn't easy. The environment itself creates hurdles like poor visibility and the complexity of tracking marine organisms in their natural habitat. Despite how advanced these robots are, they still struggle with things like blurry visuals, overlapping objects, and other sheer computational power need to process everything in real time. So while the progress is exciting, there is still a lot to work on to make these robots as effective as they need to be. And underwater environments are tricky to work with because visibility is often really low. This makes images captured underwater appear blurry or distorted, and that can mess up the accuracy of detection algorithms. Imagine trying to recognize something when you can't see it clearly. That's what these systems are dealing with. And on top of that, marine organisms tend to cluster together in dense groups, which causes occlusions. It's like a crowd of people blocking your view at a concert. The detection systems can miss some organisms entirely because they are hidden behind the others. Then there is an issue of computational power. Many existing models need a lot of resources to work, which makes it hard to deploy them on underwater robots in real time. Moreover, now while there are some solutions out here like attention mechanisms to focus on important details or lightweight network designs to reduce complexity, they are not perfect. Some of them overfit, meaning they become too focused on specific data and don't perform well on new scenarios. Others use memory inefficiently, or they struggle to handle overlapping objects properly. So the challenge here is to come up with the better systems that not only accurate and efficient, but also practical for real world underwater condition tasks. That is real world underwater detection tasks. To overcome with all these issues, this project proposes CGC YOLO, where YOLO refers to you only look once. It's a real-time object detection model. And coming to the CGC YOLO, it is basically an advanced version of the YOLO model. It is specifically designed to tackle some of the big challenges in underwater detection. And this is built to solve all the above mentioned problems. And one of this CGC YOLO's key feature is something called CSP-CBAM. So coming to the CSP-CBAM, so this is a cross-stage partial convolutional block attention module. This sounds complicated, but think of it as a mechanism that helps the model to focus on important details in an image. It amplifies the features that really matter, both in terms of where they are located and what is happening across the image. This means the model gets better at detecting things, even when the targets are blurry or hard to spot. And the other module is Ghost module. And the cool part is the ghost module. So this is all about making the model more efficient. It cuts down on the number of parameters and the model needs and reduces the amount of computation power. Basically making the whole process faster, less resource intensive. This helps a lot when you are working when you are working with robots that don't have tons of computing power to spare. And the other big issue in underwater detection is occlusion. That's when objects overlap or block each other, making it hard for the systems to figure out what it is. So, to handle this, this project introduces cluster non maximum suppression model. So, think of it as a way to clean up overlapping detections by grouping them and making smarter decisions about which one to keep up. And it also introduces the other part, that is score penalty mechanism. So this is like giving confidence scores to the detected objects, but with a twist. It adjusts these scores to ensure the truly important objects don't get overlooked even in the crowded or complex underwater environments. Together these techniques make the system really good at identifying real objects, even when when the objects are partially hidden or packed closely. And here we have evaluated the model using mean average precision, which measures how accurately it detects and localizes the objects in an image. To ensure robust testing, we have also used the data sets that are URPC 2020 and Barkish, Barkish water dataset, which which include diverse under scenarios. This helps us to validate the model performance, handling challenges like blurriness, occlusions, and varying, varying lighting. So this is the proposed system. Moving on to the extension, to further improve the accuracy of this project, we are incorporating advanced versions of the YOLO, which are YOLO V5S6, YOLO V5X6, and even the latest version that is YOLO V9. These versions are like the upgraded tools in the toolbox. They are better at detecting and handling the challenges of underwater environments like blurry images or overlapping objects. They not only improve the accuracy but also work more efficiently, which is super useful when you are dealing with complex underwater scenarios. And here we have developed a front end using Flash based framework, which makes the whole system more user friendly. Think of it like creating a dashboard where users can test the detection system easily. And to keep things secure, we also have added authentication features so only authorized users can access it. This setup ensures that users get a smooth and interactive experience while trying out the detection capabilities of the system. It's like giving the system a polished look and making it accessible to everyone in safe and organized way. Moving on to the implementation. To implement this project, we have followed the steps mentioned in the flow of work. So let's understand each of them. First, we have imported all the required libraries and modules for image processing, model training, data augmentation, and creating the front end. Then comes exploring the dataset part, where the images from the dataset are loaded into the system for processing. After that, the loaded images are visualized to understand the content and the structure. Then the images are converted into a blob, that is binary large object, which is suitable for feeding into the model, which is a suitable format for feeding into the model. Then comes defining the class. So the class labels of these objects like underwater targets are defined for detection. Then the bounding box around the objects of interest is specified. We will be specifying the bounding box around the objects of the image. Then we convert the images into NumPy array for further processing and feeding into the model. Then comes loading pre-trained model. So here the network architecture of the YOLO model is loaded and the output layer of the model are extracted for the prediction purpose. Then comes image processing, where we append the images with the annotation files. So here the images are linked with the corresponding annotations. Annotations are nothing but labels and bounding boxes here. Then we convert the images which are in BGR format, that is blue, green, and red, to RGB, that is red, green, and blue format for the compatibility purpose. Then comes creating the mask. So a mask is created to highlight or segment the area of interest in the image. Then we resize the image. So the image is resized to match the input size required by the model. Then comes data augmentation. So we apply we apply basic randomization techniques in terms of its order or appearance to create a more robust model. Then we apply rotation. The images are rotated at different angles to simulate various perspectives. And additional transformations are applied, like flipping or changing colors are applied to augment the dataset. Then comes installing the packages required. So here the required external libraries and packages are installed, such as OpenCV, TensorFlow, Flask for the project. Then comes processing the data based on YOLOs. So the data is pre-processed according to the YOLO model's requirements, formatting, bounding boxes, labels, etc. Building the model. So here, the YOLO-based model is designed and constructed, including specifying the architectures and layers. Training the model. So the model is trained on the pre-processed dataset, learning to detect underwater targets. Then the best performing YOLO version is saved for further detection. Coming to the part of frontend, a user interface is created using Flask where users can interact with the model. And a database, that is SQLite, is set up to store user information for registration and login. And users, they will be uploading images in the front end for detecting the objects in underwater, and that will be pre-processed at the backend. It will be fed to the trained model. Finally, objects will be detected in the front end, and that will be visible in the front end. And coming to the algorithms used, these are the algorithms used in this project. This is the proposed model, and these are the extension models. Extension models are YOLO V5S6, YOLO V5X6, YOLO V8, and YOLO V9. And to implement this project, we need basic requirements, which are hardware and software. So coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, backend framework Jupyter Notebook, database SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute. To execute, we are supposed to open the code folder that contains source code files. So let's open the code folder of the project. So these are the source code files in the code folder of the project. Let us understand each of them. How will they be used in this project? So we have two data sets we have mentioned right initially. So here we are using this two data sets which are URPC 2020 and brackish water data set, right? So those are the two data sets. Let's open the data set one first. So here the data set is in YOLO V5, YOLO V8, YOLO V9, and images are all in these three folders. So let's open the YOLO V5 first. Here we have images in two subfolders. One is train and other one is valid. Let's open the train folder. Here they are split in two subfolders, images and labels. First, let's open the images folder. So these are the images that are used to train the YOLO V5 model. So these are the images that are used to train the YOLO V5 model for detecting the objects in the underwater. Let's get back. And here, this label folder contains files containing annotations or labels for objects in the corresponding images. So here, each label file corresponds to an image file in the image folder. For example, this first label file, it corresponds to the first image file, which provides object locations, that is the whether it is sea cucumber, starfish, or anything, and it has the bounding box locations. Similarly, for the second image, we have second annotation file. And for all the images which are in images folder, so here total we have 610 images, right? So for all those, we will be having in 610 label files. And these label files, they follow the YOLO format. Let us open a file, for example. So let's open this file. So here each line specifies detected object. As there are three lines, three objects are detected. Here it is followed by an object class object and followed by its bounding box coordinates. This is the object class index. This is the bounding box coordinates. This is the x limit, y limit, width, and the height. Let's close this. Similarly, we will be having in all the annotation files. Let's get back. And images which are in train folder are used to train the YOLO V5 model, and images which are in the validation folder are used to evaluate the YOLO V5 model. Let's get back. And we have same images in YOLO V8 and YOLO V9. But they are annotated differently because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. Let's get back. Similarly, we have in dataset 2 also. Let's open dataset 2. So let's open YOLO V5, open train folder. So these are the images of the other data set. So these are the images. So these are the underwater images which are used to train the YOLO V5 model. Let's get back. And here we have the annotation files. And here we have validation and test folder which are used to evaluate the model. And we have same images in YOLO V8 and YOLO V9, but they are annotated differently. Let's get back. And here in the sample folder, we have images that we will be using in the front end for detection purpose. And coming to the static folder, this folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And here in the templates folder, the folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And this is the app.py file. So this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have two notebook files that are the Jupyter notebook files, which contain the combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So in this Jupyter source file, we will be loading the dataset one and we will be training all the YOLO models for detecting the objects in dataset one. Similarly, dataset two. And this is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying it. Now open the Anaconda prompt. Give the command cd, give the space and paste the copied path now. Click on enter. Here you can observe that current directory is changed to the code folder's path. Now compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. So this is the local host and this is the port. Now copy this local link generated by Flask framework and paste it in any web browser. I'm copying it. I prefer Google Chrome, so I'll paste it in that. Paste the link here. Click on enter. So this is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to get signed up first. Click on sign up and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on login and give your username and the password. Click on login. We have logged in successfully and we are redirected to detection page of the project. As we are doing two datasets, here we will be doing detection for both the datasets. So first let's do detection for dataset 1. And here you can see a choose file button, right? We are supposed to click on that for uploading the images. So click on choose file, open the sample folder. Let's open the dataset 1 as we're doing detection for dataset 1. So these are the images that we will be using now. So let's upload this image first. Click on open and now upload it. This given image, it will be pre-processed at the backend and it will be fed to the train model and then train model will be giving us a prediction. So here we got the detection. You can observe that three scallops are detected. You can observe, right? They are detected in the blue color bounding box. And this underwater image is of low light condition. You can observe, right? We cannot see everything that clearly. So in this condition also the objects, I mean the models are accurately detecting the objects. So here three scallops are detected and they are highlighted in a blue color bounding box. You can observe a class label of scallop is given and probability score is also given. With the probability score is nothing but it's the confidence level that how accurate the detection is. So let's get back and try uploading some more images. So now let's upload this image. Click on open and now upload it. So images which we are giving now, they are all of low light conditions only. They're not that clear. And in this case also the application is being correctly detecting. So you can observe, right? Two sea urchins have been detected and they are detected in blue color bounding box. Let's try uploading some more. So now let's upload this image. So here you can observe that a starfish has been detected, a sea cucumber has been detected, and sea urchins, multiple sea urchins are detected. You can observe, right? Sea urchins are detected in light blue color bounding box and starfish is in navy blue color and sea cucumber in white color. Let's get back and try upload some more. So now let us upload this one. So here we got the detection. Multiple starfishes are detected and two sea urchins are detected. So here you can observe, right? There's a starfish. And wherever there is starfish, the object, I mean, the model is detecting starfish and highlighting in blue color bounding box. And wherever there is sea urchin, you can observe, right? In light color, there is sea urchin. As it is low light image, we cannot observe, I mean, we cannot identify, we cannot see clearly that it is a sea urchin, but the object, that is the model, is able to correctly identify. So here is the starfish and here we have a starfish. So all the starfishes are detected in blue color bounding box, that is navy blue color bounding box. Let's upload some more. So now let's upload this one. Here we got the prediction. So here you can observe that multiple sea urchins are detected and a sea cucumber has been detected and with their given probability score. Let's upload some more. So now let's upload. We are uploading this image. Click on open and now upload it. So here we can see the prediction. A starfish has been detected. A sea urchin has been detected. A sea cucumber also has been detected. Three sea urchins, one sea cucumber and a starfish. So here is a sea cucumber. That is why it is drawing a white color bounding box around it. Let's get back. So now we have done with the data set 1. Let's do detection with the data set 2. So click on data set 2, click on choose file. So let's get back and open dataset 2 folder. So these are the images that we will be uploading now. So first let's upload this image. Click on open and now upload it. Here also the given image, it will be pre-processed at the backend. It will be fed to the train model. Then train model will be giving us the prediction. So you can observe, right? This image is in very low light condition. It is very dark, and here there is a fish, so it is detecting in a blue color bounding box and given a class label as fish and with the probability score. So in this case also, where in very low light conditions also the object is, I mean the model is able to detect the objects. Now let's try uploading this image. Click on open and now upload it. So here also there's a fish, so it is detecting a fish. Let's get back. Click on choose file. So now let's upload this image. Click on open and now upload it. So here you can observe that multiple objects are detected. That is a starfish. So here you can observe a starfish, right? So it is highlighted. It is detected in a pink color bounding box, and a shrimp is detected in greenish blue color bounding box, and two crabs have been detected. You can observe, right? So now let's try uploading some more. So now let's upload this image. So here multiple objects are detected, multiple small fishes are detected, and one starfish is detected, and one crab is detected. Let's upload some more. So now let us upload this image. Click on open and now upload it. So here a fish is detected and two starfishes are detected. Now let's upload one more. So now let's upload this image. So here a small fish is detected and three crabs are detected. You can observe, right? So one small fish and the three crabs are detected. Let's upload some more. So now let us upload this image. So as there are no objects here, it is not detecting any fishes, any objects in that. Click on choose file. So now let's upload this image. Click on open and now upload it. So here there is a crab and there are two crabs here. So you can observe that algorithm is detecting two objects, that is two crabs. You can observe, right? They are highlighted in blue color bounding box. Let's get back. In this way, you can check with n number of images if they are in low light condition or the dark light also. Now let's check with the graphs. Click on graph. Click on data set 1. So here we have graphs for the data set 1 where models are trained on data set 1. So this is the precision confidence curve graph, and this is the recall confidence curve graph. This is the F1 confidence curve graph. And this is the confusion matrix. This is the precision score comparison graph, where on x-axis we have precision score, and on y-axis we have all the algorithms that are trained on the dataset 1 to detect the objects in underwater. And this is the recall score. This is the mean average precision. Mean average precision, and recall are the evaluation metrics used to evaluate the detection models. Now let's check with the dataset 2. So here the first graph is the precision confidence curve graph. This is the recall confidence curve graph, FN score, confusion matrix, precision comparison graph, recall graph, MAP graph. Now click on sign out. In this way, just by uploading images to the application, whether it is of low light or dark light, in the of underwater images, the application, it will accurately detect the objects in that underwater, whether it is scallop, starfish, sea cucumber, sea urchin, crab, or anything else. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.